quickly introduce. All right, our next speaker is Dr. Liqiang of the State Key Laboratory of Astronautic Dynamics of the Zion Satellite Control Center, where he's worked as an associate professor since 2009. His research interests include space vehicle design, space mission design, filters and maneuver tracking of space debris. His talk is on orbit debris removal with laser ablative propulsion, considering epistemic uncertainties. Liqiang, you may begin.
Okay, and thanks for Professor Max and Edmondo. Thanks for all of you gave me this opportunity to attend this workshop. And sorry for my delay of the software. Okay, so this is my presentation of the orbital debris removal with laser ablation, considering epistemic uncertainties. So content, okay, so the first one is about laser orbital debris removal. And in section 2, we would like to present evidence robust optimization. And in section 3, we would like to present fidelity management in robust optimization. And finally, we give some solutions of the numerical simulation. So this is what we did in this presentation. So the first thing we did is develop a new robust algorithm with chap-shaft decomposition and the PLD techniques. So the second one is a fidelity management based on the adaptive trust region method. So the evidence-based robust optimization, basically based on the analysis of the epistemic uncertainty. So the uncertainty is kind of the interval type, can be described by a structure of the BPA. So this is the belief values of uncertainty, and this is the probability of the values. After the robust optimization, one can obtain the belief values like this one and the probability values. So this slide shows the equations we used for computing the velocity generated by the laser ablation. So the delta V equal to the product of beta Cm and phi over mu. And Cm is the coupling coefficient, and mu and zeta and the phi. So these are the uncertainties during the laser ablation removal. So the first thing, the first uncertainty from the laser ablation, and another one is from atmospheric density and from the debris itself and orbital. Okay, so to summarize the characteristics of the removal, I can find that it is multidisciplinary with epistemic uncertainty, and there are also some model available for predicting the lifetime of debris. So some of them are analytical ones with lower cost and accuracy, and some others are numerical ones, the high fidelity model with higher accuracy but quite expensive of the computational cost. So the basic idea of the robust optimization is try to optimize the objective while at the same time maximize the belief value. So the idea we used is to decompose the robust problem into a set of sub-problems with chap-shaft decomposition, and this is the framework of the new algorithm. So this is chap-shaft decomposition with different vectors, weight vectors, and this is the population decomposed with the principal components with different energy levels. So one can use the component for the generate the population in the direction of the lower energy and the high level energy. So this is the equations of the generating the new population, and so for push more forward the front in the lower level energy and extend the possibility in the high level energy. And this is the searching step. Okay, so regarding the evidence computation, given the uncertainty and the design vector, one can search the minimum and the maximum performance. And using the branching and pruning techniques, one can obtain the belief and the plausibility values using these equations, using the information from the BPA structure. So here are the application of the proposed algorithm for the designing the entry probe of the Mars entry probe. So this is the heat shield geometry, and design space consists of the geometry parameters. And this table shows the BPA structure of the uncertainties and the velocity and phase path angle, mass and density, and drag and lift jerk coefficient. And this figure shows the robust solution of the after optimization. So solution A is its belief is about 088 with the temperature about 308. Solution B, its belief value is about 0.32 with the temperature of 302. So this figure shows the solution A and B, so shows the geometry of solution A and B. Okay, so before the presentation of the fidelity management in the robust optimization, we would like to make a brief introduction of the fidelity management in the SLOO. So one of them is surrogate model, like region and response surface. So one can use this surrogate to mimic the behavior of the actual model as closely as possible, such that the computational cost could be reduced. So the accuracy depends on the number and the location of the samples in the design space. So regarding the trust region method, in this method, if the searching step is greater than the trust region, then the high fidelity model is used for predicting the improvement of the model. Therefore, the step in the trust region, the low fidelity model is used instead for reducing the computational cost. And this equation is for the trust ratio, and this is the high fidelity model, and this is for the low fidelity model. And this table shows the updated rules for the trust region size. So similar to the SLOO, in the robust optimization, the trust region ratio can be defined as this equation. The different thing is like certain direction as like this figure. Okay, so this direction is for searching the population, searching the individuals to push forward the front to the right side. And this direction, another direction is for determining the trust region. If this D1 is the trust region, if the step in the trust region, one can use the low fidelity model, and if the step outside the trust region, so the high fidelity model is used to improve the performance of the model. Okay, so finally we make some simulation of the Iridium 3 library. So the objective is to search to find the 10 candidates for some of the lifetimes could be reduced most and taking into account the uncertainties. So this table shows the BPA structure of the uncertainties of the coupling coefficient, ablation rate, and the solar radiation pressure coefficient. So here there are two models available for predicting the lifetime. One is the low fidelity model, consists of SGP4 with TLE element with B star, the drag item equal to 0.004. While the high fidelity model is a numerical one, with the solar radiation. Okay, so regarding the solution of numerical simulation, so this is after robust optimization, and this is solution A with the belief value of 0.88, and this is solution B with 0.49 with the lifetime of 3.88. So these are the parameters of the laser ablation. So number of the impulse and the frequency and the pulse rate and laser power. The velocity is delivered at the aperture and average mass with average mass and average radius. So this table shows the solution A and solution B before and after the laser ablation. This column shows the index of the debris and index and solution B, and this is the delta V, the lower bound, and the upper bound taking into account the uncertainty. So this is the belief value of solution A, and this is belief of solution B. Okay, so that's all. Thanks attention. Thanks for your attention. Any questions? Okay. Thank you very much.
I actually have a question. Have you done any analysis on the cost of this compared to other?
So do you mean that compare the cost to any other computer?
Yeah, compared to other methods.
Okay. So basically this algorithm is so we run the algorithms on a laptop. So before we run the software, we run the program. We make some samples from using the debris data set and using the numerical model for predicting the lifetime, and also did some work to establish the data set using the analytical model for predicting the lifetime of the debris. So basically, this program is running in the laptop, haven't compared with other programs.
Okay, between the two high fidelity and low fidelity, what was the difference in computational time there?
Okay, so for the analytical model, it may take seconds to predict the lifetime. While for the numerical ones, for the high fidelity model, it may take up to minutes, or sometimes may up to dozens of minutes to compute the lifetime of the debris.
Okay. Do we have any other questions? Let's take our speaker again.
Thank you very much.